Hey, what's up? So, to think about dynamics without explicit equations, I think it's helpful to start with the concept of inertia. And so, inertia is a property of matter in which essentially, if there's no net forces acting on an object in the universe, then that object is just going to keep doing what it's doing. And when I say keep doing what it's doing, I mean it's going to stay at the same velocity. The velocity is not going to change, meaning there's no acceleration. Force comes down to acceleration, at least the Newtonian concept of force. More specifically, Newton has us think about the concept of force as the inertia an object has, the propensity for it to want to keep doing what it's doing. And we use that idea and mass in Newton's second law, the whole F equals ma stuff that you're probably seeing. Well, mass is essentially a way in which we can gauge the inertia of an object. A semi truck, okay, that's sitting in a parking lot, that has a lot more inertia than a bicycle. In other words, if I wanted to push on the semi truck and get it to not be still, all right, it's going to put up a lot more of a fight than the bicycle. All right, so the semi trucks being still has a lot more inertia, i.e., it wants to stay still for the same amount of force that I give the semi truck versus the bicycle. It's going to be a lot easier to get the bicycle moving. So when you see the mass in Newton's second law, that essentially is the whole concept of inertia. And so objects with more mass have more inertia. And so here's the thing, we also have this concept of acceleration, which builds on the kinematic ideas that we've talked about. And remember, you have the notion of position, you have the notion of distance between two different positions, and then you have the notion of, like, well, what if I travel a certain amount of distance over a certain amount of time? That's the velocity concept. But then you have the idea of, well, maybe my velocity is going to change. I'm going to travel different amounts of distance over different amounts of time. That's acceleration. So you have position, velocity, which is a measure of position over time, and then acceleration, which is a measure of velocity over time. All right? So let's start with an object that's just sitting there at rest. If there are no net forces on that object, it's just going to continue to be at rest. Because when it's at rest, it means that its velocity is zero. So if there's no net acceleration, that means the velocity doesn't change, which means if velocity is at zero, then it's going to stay at zero and stay at zero and stay at zero. So it's just going to sit there. Okay? Here's the thing, though. I've learned that some students get a little confused when they think of the concept of force. They associate it with motion, and more specifically, if an object is moving in a particular direction at a particular time, there must be some net force in that same direction to make the object go in that particular direction at that particular time. Now, here's the thing. You can have an object that's moving in a direction with some non-zero velocity. And if I have no net forces on that object, that means that there's no net acceleration on that object, which means that the velocity doesn't change. But you can have a non-zero velocity that doesn't change, which means you can have an object moving in a particular direction. Insofar as the velocity in which it's moving doesn't change, there's no net force acting on it. So you can have an object moving through space, even though technically there's no net forces on the object. Now, granted, there had to have been some initial force to get it moving in that direction, but at some time later, if you account for all the possible forces acting on the object and there's no net force, that means there's no net acceleration, which means that there's no change in velocity over time, which means that the velocity is constant. So if you can have also a object moving at a non-zero velocity that actually technically doesn't have any net forces on it. Another thing people get confused with is that you can have an object that's moving in a particular direction, but actually the net force is in another direction. Okay, so if you've got an object that's moving in one direction, there could be a net force in the other direction, and that means that the velocity is changing in the other direction, which means that it's slowing down in the original direction. So, in other words, You can have deceleration, where your object is moving in one direction, but the net force is actually in another direction. And some component of that is totally opposite of what the current direction is, right? So it's possible you can have an object moving in one direction and actually the net force is in the opposite direction. So don't fall into the trap of thinking that if an object is moving in one particular direction, that there must be a net force in that particular direction. It's possible that it doesn't have a net force at all, in which case it just keeps moving in that direction at a constant velocity. Or it's possible that the direction it's going, the velocity is slowing down in that direction, meaning it's accelerating in the opposite direction, meaning it's decelerating given its current direction. Okay? So, inertia, a property of matter, objects at rest, if there's no net force, they just want to keep at rest. So objects at rest tend to remain at rest. Meanwhile, objects in motion, if an object is moving through space and there's no net force on it, that means that the velocity doesn't change, so it just keeps moving through space at the same velocity. So objects in motion also tend to remain in motion. So what I'm talking about right now is often called Newton's first law. And then I talked about the concept of inertia and the concept of acceleration. Newton's second law is the idea that force is the combination of inertia and acceleration. I also want to tell you about Newton's third law, and that's the idea of action-reaction pairs. So think of like I take a hand and I push it against the wall. So when I do that, I feel in my hand when I'm pushing against the wall, I feel a force of the wall pushing back on my hand. And so put this in words, every action has an equal and opposite reaction. So if my action is pushing against the wall, the reaction is the wall pushing against my hand. So Newton's third law again, for every action, there's an equal and opposite reaction. So if I was pushing against the wall, I could represent that force as a vector, where the length of the vector is proportional to the amount of force that I'm pushing on the wall, and then the arrow part of the vector is pointing in the direction that I'm pushing. Well, you can imagine that since I'm feeling something when I'm doing the pushing, that something being the wall pushing back on my hand, you can also draw a vector of the force of the wall acting on my hand. And that's going to have the same exact length as the force of me pushing on the wall, but the arrow is going to be pointing in exactly the opposite direction. So you can imagine for every action, there's an equal and opposite reaction. For every force representing a vector, there's going to be a reaction vector pointing in exactly the opposite direction. And so that's Newton's third law. So when you're solving problems about dynamics, that is, you're solving problems that involve force, I think what's helpful to do, especially because you're dealing with these vectors, is you start with your object of interest and represent that on a piece of paper with a dot. Okay? Technically, we'd say that dot represents the center of mass of the object, but just for simplicity, just put a dot on a piece of paper and pretend that's your object. Whether it's a box or a car, a semi-truck, a bicycle, just represent it with a dot. Assume that all the mass of the object is within that dot. The next thing you need to do is you need to read the problem carefully, and you need to think about what are all the different forces that are acting on the object. Remember, that object, when it's in motion, it tends to remain in motion. When it's at rest, it tends to remain at rest. The more mass it has, the harder it is to alter either one of those. So then what you need to do is you need to draw arrows, i.e. vectors, that are in the direction of the various forces involved in the problem, where their lengths are proportional to how big those forces are. So draw arrows emanating from your dot on the piece of paper, okay? Now, if the vectors representing the different forces don't nicely align perfectly in either the horizontal or the vertical direction, no worries. What you can do is you can take the vector and you can decompose it into its horizontal and vertical components. So what you would want to do is make sure that you account for every possible vector, accounting for every possible force, and then any of the forces that aren't nicely in the horizontal or vertical direction, break them down into a component that's in the horizontal and a component that's in the vertical. So now when you have everything in the vertical direction and everything in the horizontal direction, you essentially have two equations. You have one equation in the vertical direction where the sum of all of the vertical components of force are equal to the mass of the object, that's the mass represented by that single dot on the paper, multiplied by the acceleration of the object in the vertical direction. And then the second equation would be, if you sum all of the components of the forces in the horizontal direction, then that would be equal to the mass of the dot again, the center of mass of an object is represented by the dot on the paper, multiplied by the acceleration in the horizontal direction. So this will allow you to figure out how much acceleration is going in the horizontal direction, along with how much acceleration is going in the vertical direction. And then you can put Humpty Dumpty back together again. You could combine those back to figure out the direction of net acceleration, which gives you the direction of net force. And bringing things full circle, okay, the direction of net force is not always the same thing as the direction of motion at that given time. It's possible an object can be moving in one direction and there's no net force on it, and so it just keeps moving in that direction at the same velocity. That is, the velocity doesn't change, meaning that there's no acceleration. And remember, you need acceleration for force. Or you could have a situation where an object's moving in one direction, but it turns out the acceleration is actually in another direction, meaning that the velocity in the current direction is getting less and less, which means it's accelerating in some other direction, which is to say it's decelerating in the current direction it's going. So don't think that just because something's moving in one particular direction that the net force is in that direction.